Well, thank you for the introduction, and a huge thanks to the organizers for having me here at this wonderful conference. So this is work in preparation with Mario Garcia Fernandez. And actually, unlike what the title of my talk suggests, we were not initially interested in the moduli spaces of Calabi-Yau metrics, but in a moduli space of more general equations that involve also a connection on a principal G bundle for a GR reductive group. However, it turns out that most of the more interesting features of this moduli space already appear when we take the group to be trivial, and so we simply forget about the bundle. And it is in this situation that we simply get a moduli space of Calabi-Yau metrics. And so this is what I'm going to talk about, but in a relatively different way than what the literature usually deals with. So for starters, let's just do a primer on what a Calabi-Yau metric is and their moduli spaces. So there are many definitions for what a Calabi-Yau metric is. And for me, I typically think of a Calabi-Yau metric as a Riemannian metric on a smooth manifold of dimension 2n, which has holonomy exactly equal to the group SUN. So these moduli spaces have been studied in many different contexts, ranging from mathematical physics and especially in relation to mirror symmetry, to algebraic geometry with moduli spaces of polarized Calabi-Yau freefolds, for example, and also simply in the context of moduli spaces of Einstein Riemannian metrics on a compact manifold. And most of the time, the way that we study these moduli spaces is through Yau's theorem, which allows us to understand the Calabi-Yau moduli, locally at least, as the product of the moduli space of complex structures, that is a Teichmüller space, and a moduli space of Kähler metrics. This was already understood by, for example, physicists and Candelas and Llosa in 1991 when they studied moduli spaces of Calabi-Yau manifolds. To make this more precise, the fact is that you can recast the Calabi-Yau metric into the data of a triple, which is a J, a complex structure on M, so an integrable complex structure, then a homomorphic volume form on our complex manifold, and a Kähler form, which is the contraction of our metric, our initial metric G, and with J. And these are asked to satisfy this normalization condition right here, which is pretty much the condition that tells us that our Kähler form is actually Kähler-Ricci flat. And so the content of Yau's theorem that came out in '78 is that if we have a compact Calabi-Yau n-fold, that is, if we have a complex manifold of dimension n with a holomorphic volume form, then on each Kähler class that satisfies this equation at the level of cohomology, so if you will, if we put an integral before each of the expressions that we have inequality, then under those conditions, there is exactly one Kähler metric inside this cohomology class that satisfies this equation. So more informally, on each Kähler class, there is exactly a unique Kähler metric, Kähler-Ricci flat metric. And the way that we commonly think of this is that if you consider the moduli space of Calabi-Yau metrics, if appropriately defined, then it fibers over Teichmüller space with fibers which are equal to the 1-1 homology of M, which under the hypothesis of a holonomy SUN is exactly equal to the second cohomology with complex coefficients. I will explain what I mean by appropriately defined in a few slides. Now, what we're going to do is something a little different, which is to not use Calabi-Yau's theorem, and just directly study this modular space without any separation of variables. And more specifically, being inspired by the work of Attila Bots, we would like to actually realize this space as a symplectic reduction. As it turns out, by trying to do this, we're going to encounter a few unusual problems. First, a problem that comes with a group action on a space which is going to be by a real Lie group, but which is going to have at least partially complex orbits, similarly to what a presentation by Brian Collier found out, I guess, or maybe not. And we're also a phenomenon related to higher symmetries and also related to generalized geometry. Okay, so let us move on with the construction of our moduli space. Now, again, a naive definition of our moduli space might be simply take the space of triples that I defined previously and take them up to the action by the diffeomorphism, by the identity component of the diffeomorphism group. However, this is in some sense not a good definition because this space of parameters is not symplectic or complex in any natural way. And what was already understood by physicists is that in order to make this space complex or symplectic is to complexify the Kähler form by using a B field that is simply a real two-form B. And this actually adds the directions in our parameter space that are necessary for it to support a complex structure. So now, let's just simply define our space of parameters P, which is a space of triples right here. And we want to actually endow it with a complex structure, which I already said is actually possible. So how to actually do it? The way to do it is by using generalized geometry, which was introduced by Hitching. So consider the sum of the tangent bundle with the cotangent, which we typically call the generalized tangent bundle, and simply endow it with a pseudo-Euclidean metric, which is roughly given by simply the duality pairing. Then in this context, we can interpret each B field as a symmetry of our generalized tangent bundle. That is an orthogonal automorphism. And using these B fields and more generally complex B fields, which make sense if you complexify the tangent bundle, we can identify this set right here of tuples given by an almost complex structure and a complexified Kähler form with a certain set of isotropic subbundles of our complexified generalized tangent bundle in this way right here. By using this bijection, we can actually endow this space L with a complex structure, simply by noticing that on each point of our manifold, this is simply an element of the orthogonal Grassmannian. That is simply a isotropic vector space with respect to the pairing, complexified pairing right here. So we can actually write down a formula right here by using this bijection, which looks like this. And now to actually get a complex structure on our space of parameters P, we need to actually also include what happens with the variation of the holomorphic volume form. To do so, simply notice that if we look at the map right here, then the fiber above a point is simply an open subset of the complex vector space, which is of course naturally an infinite dimensional complex manifold. So in order to actually define our complex structure J on P, we'll simply define it as the only complex structure such that we obtain a holomorphic map by forgetting the holomorphic volume form, and that on the fibers we get the obvious complex structure. So explicitly, it's just a complex structure right here. So we have finally defined a space of parameters as a complex manifold. However, what it is customary to do is to actually forget about the scaling of the holomorphic volume form. So we will instead consider the space given by the quotient by scaling of C star. And in this situation, Z is an infinite dimensional complex manifold, and the projection, the canonical projection, can be thought of as a holomorphic C star bundle that is pretty much a holomorphic line bundle on top of it. And now, if we have a holomorphic C star bundle, then by defining the Hermitian metric on it, we, as usual, can actually obtain possibly some forms of Kähler structures on it. So this is what we are going to do. So we consider the following functional referred to in the literature as the dilaton functional, which was initially used by Garcia-Prada, Rubio, Shabazzi, and Tipler, and then repurposed by physicists Ashmore, Strickland, Constable, Tennyson, and Waldron. And as it turns out, this defines a Hermitian metric on our holomorphic C-star bundle. Since when we scale the holomorphic volume form, then you simply get the homogeneity of degree 1 for this functional. Okay, so let's just define our form as I times the curvature of this Hermitian metric. Or if you will, if you want to be more precise, perhaps use this formula right here. Then this is, of course, a real 1-1 form. And the fact is that it is actually non-degenerate. However, it is not actually a Kähler form because its signature is indefinite, similar to the problem that Brian Collier encountered. And this is what is going to produce a lot of weirdness later down the line. And the reason why I talk about pseudo-Kähler reduction and not Kähler reduction. All right, moving on. Now, I already have a symplectic manifold, which is simply the pseudo-Kähler manifold that I already defined. So you might expect that what I simply need now is a group that acts Hamiltonianly. However, before that, we need to come back to the physics a little and realize that a moment map is not enough to actually recover a Calabi-Yau structure on our manifold. Specifically in heterotic string theory, there are two types of equations that imply supersymmetry. And so in this situation, a Calabi-Yau metric. And these are the D-terms equations, which are actually the vanishing of a moment map. But there are also the F-term equations that come from imposing that our point is a critical point of what we call a superpotential. In our situation, the F-terms look like this, where we have fixed a free form, commonly called the NS flux, which is just a closed free form on M. So they involve imposing integrability of the complex structure and a certain equation that couples the complexified Kähler form with H0. More importantly, these equations are actually equivalent to imposing integrability, invertibility, if you will, of our subbundle of the complexified tangent with respect to this bracket, which is called the twisted Dorfman bracket. Now, the importance of this bracket is that it actually defines, together with the pseudo-Euclidean structure on our bundle, complexified tangent, the structure of what we call a Courant algebroid. That is simply a vector bundle with a pseudo-Euclidean metric and a bracket on its sections, and also a projection on the tangent, such that these axioms are satisfied. In particular, we don't have a Lie algebroid in general, because this equation right here tells us that what makes this bracket antisymmetric is exactly measured by the pseudo-Euclidean metric. Okay. Now, finally, for the symmetries, since we have added an extra field that corresponds to the B field, we expect that the actual symmetry group is going to be changed from the identity component of diffeomorphisms to some kind of extension of the diffeomorphism group by the closed two forms in such a way that we get a group that acts naturally on a space of parameters Z. It turns out that from generalized geometry, a group that fits a bill is simply the group of the identity component of the automorphism of E. That is, the automorphism of E as a vector bundle, possibly covering a diffeomorphism in general, not necessarily the identity. And these must preserve the metric, the bracket, and the anchor. It turns out that we're also going to need assignment groups, so let me introduce it too. For starters, the Lie algebra of our group, G, is simply a certain set of differential operators, covariant differential operators, that preserve the bracket and the anchor in some sense. And we'll consider Lie subalgebra, which is given by the inner derivations, which are simply given by taking the bracket with a given section, and consider the subgroup H of G that is generated, that integrates this ideal formally, since we are in infinite dimensions. Then this group formally appears as an extension of the diffeomorphism group, this time by the exact two forms on M. Now, finally, we're ready to talk about our moment map. Now, via this correspondence, G naturally acts on our space of parameters, and it acts also in a way that is linear on P and by holomorphic isometries, and it preserves too the solutions of the F-term equations. So we are ready to state our first theorem, initially due by Ashmore, Friedland, Constable, and Wandram, and then later more rigorously checked by Garcia-Fernandez and me, which tells us that the action right here is Hamiltonian with a moment map. And moreover, if we consider the restriction to the action of H and to the integrable elements, then we recover a particular set of equations right here, that is holomorphicity of omega, and an equation that couples the Kähler form with the holomorphic volume form. This actually generalizes a result that was already known by Garcia-Fernandez, Rubio, and Tipler, who was published in 2024, but who actually appeared earlier than the work by Ashmore, Strickland, Constable, and Wandram in the archive. Now, of course, the fact that we actually have a moment map is not very surprising, since we have a linearization of the action. And in that situation, we can simply define the moment map in this way, where we have chosen a point above the point that we are considering. And the fact is that this choice at the end doesn't matter for the formula. Now, of course, these equations do not look exactly the same as the ones that we would expect for a Calabi-Yau metric. However, luckily for us, they actually are equivalent, and let me explain why. This equation is simply, by taking the Hodge star, this exactly equivalent to this one, where we have rescaled the Kähler form in this way. We commonly refer to these types of metrics on complex manifolds as balanced. And so we say that omega is conformally balanced. This is in general a much weaker condition than being Kähler. And you can think of it actually as a dual condition to being Kähler, since instead of being preserved by taking submanifolds, it is actually preserved by taking quotients, or more generally, the image of a surjective holomorphic submersion always admits a balanced metric when the domain admits one. However, in this situation, we actually have a stronger condition than just being conformally balanced. And this comes down to the F-term equations. So if you remember, the F-term equations look like this. So simply by differentiating this right here and using the fact that H is closed, we take D, and then we get 0 minus 0 plus BDC omega equals 0. And we refer to these metrics as pluriclosed. And it was work by Ivanov and Papadopoulos that showed that if we have a conformally balanced metric, which is also pluriclosed, then it's actually a Kähler metric. So we actually get a reduction then of the holonomy to SUN. However, we cannot rule out the possibility that we actually get a smaller subgroup than exactly SUN. We can obtain this condition maybe by imposing, for example, irreducibility and certain cohomological conditions. But for us, this is already good enough. Right. Now, we want to actually, we have actually obtained in this way the symplectic interpretation of the Calabi-Yau moduli space. And now we're going to move on with the construction of the moduli metric. This is the main advantage of working in this way via the differential geometric considerations. And the importance of this relates also to possibly mirror symmetry, since mirror symmetry hypothetically would correspond to local isometry of our moduli space. And so in order to consider local isometries, we need a metric. So let's talk about how we actually proceed to construct this metric. Now, consider simply a symplectic quotient by H, and we want to construct a Pseudo-Kähler structure on it. Of course, we already know that at each point, the tangent space is naturally, at the very least, pre-symplectic, which that is possibly, it has a natural two form that is possibly degenerate, and the symplectic structure is simply induced by the classical theory of symplectic reduction. Now, to actually do this, now to construct our Riemannian and complex structure on our moduli space, since we are in infinite dimensions, there may be a lot of subtleties involved, and let me tell you a little bit about how this works. Now, in general case, consider a possibly infinite dimensional Pseudo-Kähler Hamiltonian G space, Z, with a Kähler form omega Z and moment map mu Z. Then let's just consider the infinitesimal action P and the differential of the moment map in such a way that we obtain a complex that at least formally gives us the tangent space of the Hamiltonian reduction as simply the cohomology. Right. Then, in the nice situation, we have an orthogonal decomposition right here. And in such a situation, we can identify a cohomology with this intersection, which is simply a subspace of our tangent space. And so we get, in this way, a Riemannian structure here. And so equivalently, also a complex structure, since we already know that this has at least a pre-symplectic structure in a natural way. This works, for example, if we are in a situation where our manifold is finite dimensional Kähler. And we can also make it work if we are in infinite dimensions in the situation where P is a differential operator between vector bundles. And if we consider the P star composed with P, then we get an elliptic operator of index 0 with kernel equal to 0. It is usually the case that if this actually works, then this condition holds generically. All right. We have a slight problem right here, however, which is that for starters, our Lie algebra contains the exact two forms on M, if you remember the exact sequence that I wrote earlier. And so it is not a vector bundle. However, the way that we define it makes it very much related to a vector bundle, or at least to the sections of a vector bundle. That is, taking the bracket, the twisted Wolfram bracket, gives us a map from our sections of E to our Lie algebra in such a way that we obtain a sequence right here. So in a review of higher geometry, this suggests that we should actually think of our Lie algebra not as this, but as the sequence right here, as this arrow from the smooth functions to the sections of E. So having understood this, we are actually going to replace our moment map with what we refer to as a higher moment map rather informally, which is going to be determined by simply a map into the sections of E, such that it is determined by the original moment map and a certain explicit non-degenerate pairing, which is simply given by this formula right here. So we paired up two sections after twisting them by the B field. And the formula is simply the one that you would expect. We first normalized using the dilaton functional. And we later pair up the vector field, the forms, and we multiply by the same volume form that appears in the dilaton functional. Right, so this gives us what we call the higher mode map, and we're still trying to figure out the formal properties that this should satisfy. It is a little similar to the notion of generalized moment map that Bernstein, Cavalcanti, and Gualtieri worked on. So we're still trying to figure this out. An important thing that I didn't mention earlier too is that this sequence right here is actually what we call the Lie-2 algebra in a very concrete sense. That is, it has a bracket such that the Jacobi identity holds only up to homotopy. And this is due to work by Reutenberg and Weinstein. Now, we can finally construct our complex as a complex of sections of vector bundles, which is obtained simply by taking the infinitesimal action composed with the map that goes from our sections to the algebra, and L, which is going to be the differential of our higher moment map. Then the cohomology again is going to model the tangent space of our moduli space at the equivalence class of the point that we have fixed. Now, of course, I am lying a little bit here because the way that I define Z0 makes it pretty clear that this is not a vector bundle. However, it is easily related to an actual vector bundle, which is this one. The subtleties that come with this are not really very important for the exposition, for the sake of this exposition. So I will just ignore them. However, there is another problem which is more problematic for the construction of our metric. It has to do with the infinitesimal complex orbits that I mentioned earlier. So in order to look at this problem, let us define this subbundle of our generalized tangent, which is given in this way. So explicitly, you can write it down using the metric and the B field. Then this B plus, just by definition, has a complex structure, which is simply multiplication by I on L and by minus I on L bar. And the important thing right here is that if we rotate by J and then take the infinitesimal action, then this is equivalent to taking the infinitesimal action and then rotating by J. So somewhat, we have found a piece of our Lie algebra that acts as if it were a complex Lie algebra, even if our group initially is only a real group. I would also like to point out that this is very much analogous to what happens when we act with the diffeomorphisms on the space of integrable complex structures. The infinitesimal action is just taking the Lie derivative, and the fact is that if we rotate by J and then take the infinitesimal action, then it corresponds to taking the infinitesimal action and then rotating by J. So you should think of this as pretty much the analog of the Lie algebra of the diffeomorphisms. The upshot of this formula is that taking the infinitesimal action by any section of V plus gives us a vector in a tangent space which is orthogonal to the entirety of the kernel of the differential of the mode map. So, more importantly, what we get is that this space sits inside the intersection of the image of the infinitesimal action and is orthogonal. And it is in general non-zero, so this space cannot ever be in direct sum. And this poses a problem immediately for trying to define our metric. However, we can perhaps try to deal with this by using a reduction by stages procedure. The idea would be to try to reduce by P plus So in order to do this, consider again the orthogonal decomposition, where V plus is the one that we defined, the bundle that we defined earlier, and V minus is its orthogonal, which is given by the same definition, except that we replace the plus by a minus. Then, by analogy with this action on our space and the infinitesimal action of diffeomorphism on complex structures on M, we might think that of this sequence of vector spaces as a higher analog of the sequence that is obtained by differentiating the exact sequence right here that defines our group H. So as you see, we have a problem right here because this is actually the thing that we want to reduce by before, even though it is actually the quotient group and not the normal subgroup. Anyway, now how does this look like at the level of the moment map? Okay. Again, consider a point. And then we have an explicit formula for the higher moment map right here, where eta is simply the form that is pretty much determined by the derivative of omega. Thus, in this situation, if we look at the definitions for what V plus and V minus actually are, then if we decompose our moment map with the plus and minus parts, then we see that the plus part pretty much corresponds to, well, this part right here, and the minus part actually combines this differential of our holomorphic volume form and the other equation that we obtained earlier. In particular, if we impose the moment map condition first by plus, we get a holomorphic equation in some sense. In total, we can define then our complexes in such a way that we impose the equations given by the plus part of the moment map first and then by the minus part. And in such a way that we actually recover our cohomology, that is the tangent space of our moduli space in the end. And then by the comments that I made earlier, the cohomology of this complex, which appears again right here, is actually endowed with a metric and a complex structure after passage through the quotient. Now, what we would expect is that this operator right here would be elliptic, but it actually isn't. That is, what we want to do is remind you to define a metric, and since we already have a metric and a complex structure right here, then we might expect that we can simply do what is typically done, since we have already gotten rid of the bad symmetries somehow earlier. However, this operator is not elliptic, and this fact has to do with the higher symmetries that we haven't taken into account. So now, including the whole Lie algebra, if you will, of our group of symmetries, we see that our complex can be extended to a complex like this. And accordingly, we can also extend our complex S minus by taking into account this differential rate here, which is just the projection of this map with the orthogonal projection on V minus. And then we can finally define the actual operator that is going to be a nice one, that is a second order elliptic differential operator right here. Now, what does this operator actually look like is a question. We can also, it turns out that we can define a natural Hermitian metric and a natural holomorphic structure on the complexification of V minus, such that under some identification that I will not write down, the formulas look like this. So they're very simple. And then let's just consider the Dolbeau operator associated to these structures right here and the Kähler form omega 0. Then it turns out that our operator that we defined earlier and this Dolbeau operator are equal. In our situation, actually, since the moment map vanishes, we already argued that the form has to be Kähler. So the formula for our our Dolbeau operator simply looks like this. That is, V minus times C star is isomorphic to the direct sum of the holomorphic tangent and cotangent. And moreover, by Ricci-Klattner of omega under Weizenbach identity, we can show that the Dolbeau operator right here is simply equal to the Hodge Laplacian. So delta minus is equal to the Hodge Laplacian. Having done all this, we can finally, using all of this, we can finally prove the result that we need, which is that at each point where the mode map vanishes, we have an orthogonal decomposition of the middle part of the cohomology of the H minus complex, which is, I remind you, is H1 of S star plus. Then again, in this situation, we can simply identify the cohomology that is, or of our original complex, which is thus a tangent space of our moduli space, with a subspace of this space right here. And again, this subspace has a complex structure and a possibly degenerate pseudo-Euclidean metric. In total, we get a complex structure and a metric compatible with a symplectic structure on H1. Now, I say actually, if you read carefully, I am saying symplectic structure and not pre-symplectic, and a metric and not a degenerate metric. And this is because we can actually compute this metric and show that it is non-degenerate. So let me tell you a little bit about that. There is actually an isomorphism of this cohomology with certain Dolbeau cohomology groups in such a way that we can explicitly write down our metric as the metric being the one that satisfies this formula. Here, we simply have the Weil-Petersen metric that is related to deformations of the complex structure. And then we have a term related to contraction by the Kähler form. And then we simply have the polarization induced by the Kähler form omega right here. So we have a positive definite part and a negative definite part. More importantly, if we actually have a true Calabi-Yau metric, that is, if the holonomy is actually equal to SUN, then it turns out that this cohomology group vanishes and we get a positive definite metric on a moduli space. And it is not very difficult to show that this is the same metric as the Candelas de la Osa metric that is obtained from the modified metric that separates the Kähler variable from the holomorphic variable. Now, this is a very nice story, but as I explained earlier, there is a more general story that comes from a more complicated set of equations. So since I still have some time, let me explain you how that works. We're going to talk about then the whole Schrödinger system. Now, for a little bit of context, generalized geometry is particularly well equipped to deal with equations not just in Kähler geometry, but in possibly non-Kähler geometry too. In particular, we have the whole Schrödinger system, which is a system of equations that is pretty much analogous to the equations to the Calabi-Yau equations, but for non-Kähler manifolds. So to actually explain give you what the equations are, let me fix a compact Lie group K with a symmetric non-degenerate invariant pairing on its Lie algebra. We also consider a principal K bundle above M such that the first pointer in class associated by term 1 theory to P vanishes. Then, by definition, we can fix a connection on P and a free form on M such that we have this identity right here. And as it turns out, this data determines a special Courant's algebra over M, which is not the generalized tangent bundle anymore, but it is this bundle right here where we have added the adjoint bundle of P. Right. We will consider the parameters which are given by an almost complex structure, a holomorphic volume form, a complexified Kähler form, and a connection. So these are as before, and then we have added our principal connection right here. And this whole Schrödinger system looks like this, set of complicated equations. Don't worry too much about the exact form of them. Just notice that we have a few familiar equations right here and also right here. Importantly, also very importantly, this equation right here, which is analogous to the one that I wrote over there, which was part of the F-term equations, does not imply anymore that our form is pluriclosed, since H0 is not necessarily closed anymore. And we have this extra term right here. Right. Now, to actually understand this again as a symplectic reduction, we proceed in pretty much exactly the same way. That is, we define a Z, which is the space of parameters, where again, we implicitly assume that omega is taken up to scaling. And we consider L, where we have removed, that is forgotten about the holomorphic volume form. And these are again infinite dimensional complex manifolds where the structure is determined, where the complex structure is determined by correspondence between the objects of L and certain isotropic subbundles of our complexified Courant algebroids. Moreover, the first equation right here of this system is actually equivalent to imposing evolutivity of our subbundle L bar. Now again, on Z, we can define a pseudo-Kähler structure, which is determined by the dilaton functional. It's exactly the same functional, except that now we have an extra parameter that does nothing. And for the symmetry group, we're going to consider a certain group of automorphisms, of Courant automorphisms, which actually appears as the central group in an exact sequence right here, and which acts naturally by holomorphic isometries, preserving the subset of solutions. This is just directly from the definition, pretty much. Now, again, we can show that the action is Hamiltonian and it has a moment map, such that if we restrict to the action of a certain subgroup, which is H, and consider only the integrable liftings, that is the involutive L bars, then the vanishing of this moment map is equivalent to the second column that we saw on the Holz-Schrödinger system. Let me show you again, yes. This column is exactly the same as this set of equations right here. So the result that I presented earlier is actually more general, which something that was already known by Garcia-Fernandez, Rubio, and Tipler for a fixed complex structure, and was later generalized for moving complex structure by Ashmore, Julian Kosellev, Tennyson, and Waltran. Now, let us proceed again to try to define the metric. So we just pick a point, which is a zero of our moment map, and so a solution of the Holz-Schrödinger system. Consider the corresponding subbundle of our complexified Courant algebroid and the corresponding orthogonal decomposition with a V plus and V minus defined in this way. Then again, we can define a higher moment map and so define a corresponding pair of complexes and also a second order differential operator on V minus, which I remind you is the actual operator that will allow us to prove that we actually have a metric on our space. Now, on the other hand, we also have a different operator on V minus complexified, which appears again by identifying a special pseudo-Hermitian structure on V minus complexified and a certain Dolbeau operator, which explicitly look like this in a certain splitting. Then again, if we consider a corresponding Dolbeau Laplacian, as it turns out, we don't get equality anymore, but we get equality up to multiplication by a non-vanishing smooth function. So in the end, in that the result that we actually want, which is that the kernels of these operators is actually the same. Now, for our results, if we actually assume that the dimension of the kernel of this operator is the first Betty number of M, then we again get an orthogonal decomposition. So the theorem again that we had earlier is more general. That is, this condition was automatically satisfied before, but now we need to impose it. We obtain then the corollary as before, that the tangent space inherits a natural complex structure and a symmetric bilinear form, which are compatible with expressive symplectic structure. However, we don't know if it's actually non-degenerate now because we cannot actually effectively compute it. Finally, we also get final results that you should think of the analog as an analog of an infinitesimal version of the Donaldson-Uhlenbeck-Yau theorem, which is that we actually get, again, this condition right here, together with vanishing of the 0-2 Dolbeau group and the fact that the del-del-bar lemma holds. Then in that situation, we can identify the tangent space with the cohomology of this holomorphic vector bundle on M. This is a fact that on the assumption of this hypothetical correspondence between solutions of the Haustrominger system and certain stable objects was proved by physicists De Llosa and Svans. And then further work by Ashmore, De Llosa, Minassian, Strickland, Kosterborn, and Svans further use this to actually construct a certain L-infinity algebra of deformations for the Haustrominger system. So now, having presented all of this, there are of course a bunch of questions that you could still ask relating to, for example, is the metric that we obtain actually non-degenerate? What is the stability condition? That hypothetical stability condition? And the answer is we don't know yet. But more importantly, and the part that we are now focused on, is to try to understand this strange procedure, which is we call an upside-down reduction by stages. So if I may, let me leave you with that thought. Thank you.
Thank you. Any questions? Let's see. We've got a mic anyway.
There's some work by Joel Fine on trying to understand the Einstein equation as a moment map, but that's not in this like generalized geometry complexified Kähler classes sense. Is there any relationship between what he was doing and what you're doing?
I'm not familiar with that work at all, actually, but that might be very interesting to read on. You know. Thank you.
I can give you the reference over.
That would be great. Thank you.
Yes, so I was wondering if your momentum map picture has given any cue on the case stability or on the stability you can expect for this issues. Or I was wondering.
Can you speak a little louder?
Sorry. So I was wondering if your momentum map picture for the whole Haustrominger system was giving you any cue concerning the case stability or the stability you would need.
That's a great question. Thank you. Actually, the reason that we were interested in this problem is to actually come up with a new stability condition, because the previous work did not actually give us an interesting one. But as it turns out, this doesn't actually give us anything either. As in, if we actually create the Futaki type invariant for this mode map, then under very mild conditions, say that the volume form is holomorphic, then you get that the Futaki invariant vanishes identically. So unfortunately, we don't get any new stability conditions. And it is actually a conjecture by Yau that there are no new stability conditions except the obvious ones that you get from just looking at the Haustrominger system. So this is still unresolved.
Yeah, so for your moment map, I mean, do you consider some gradient flow that, I mean, does that give you a natural flow to consider for the Haustrominger system?
Well, there is definitely a relation with flows right here. I'm not sure if it's the gradient flow of a certain map, but there is a flow interpretation due to Garcia Fernandez, González Monita, and Streets that considers pretty much the same roadmap that we have right here with a slight modification, and then produces a flow that in theory would produce possibly solutions of the Haustrominger system. It's referred to as they refer to it as pluriclosed flow. So there's that.
Luis had a question.
Doesn't matter. In the Calabi-Yau case, the first case,
Yes.
you also have a symplectic reduction construction, right?
Yes.
And you also need this upside down process.
I think we do.
Can you explain a bit?
I mean, okay, you want me to be a little more precise, maybe, or okay. So again, if you remember, we had our complex, which is just called S star, which is simply given by infinitesimal action, then a tangent space of our manifold, and then again, sections. And we realized that if you look at the sections of V plus, then we obtain a subset right here, which is null when we pair it up with sections of the kernel of this operator right here, L. So what is commonly done in this situation is that we simply first take the quotient by this subspace, you know? The problem is that it seems that this subspace is actually analogous not to the Lie algebra of a normal subgroup, but to the Lie algebra of the quotient group. That is, this would be the Lie algebra of G quotiented out by, sorry, H quotiented out by exact forms. So this poses a problem for trying to interpret this geometrically, because this does not act on our space.
This is infinitesimal.
Yes, this is at the infinitesimal level. The only reason that we can do this, that is actually make this act on here, is because we're working infinitesimally.
Yeah, what happens? But you can't give any.
No, at the moment we don't know what is going on.
Rui, you had another question?
Oh, yeah, just going back to what Evelyn was asking about the analog of case stability, I just wanted to point out that in the Calabi-Yau case stability still does have some content, even though you can solve the Monge-Ampere equation. It actually restricts the singularities, so it's vacuous in the smooth case for smooth Calabi-Yaus, but it actually implies that the Calabi-Yau, if it's case stable, it must have these KLT singularities, so there is some content, even if it's not.
Okay, thank you.
Any more questions? Okay, well, let's thank. Okay, lunchtime.